Good morning again, y'all. I've got everyone's names and the attendance updated. Today we're going to continue our conversation though with these limits. All right, I wanted to make sure to do a little bit more of the limits before we jump into the rate of change, just to make sure we have everything in place as far as what we might need it for during this course. What we're going to find is limits is the foundation of a lot of stuff as far as discussing things in calculus, but it's not something we're going to have to use all the time in our class. Okay. But I still felt like these few things I'm going to cover today are going to be important. So for this first graph, though, I had us focus on two different X values. You'll see here the first group, I wanted to focus on X approaching -3. And the second group here, we're approaching -1. Okay. One thing that I want to remind you, though, as you deal with limits, for instance, when we look at X approaches -3 from the left here, we're not evaluating the point itself, right? This is not function evaluation. What we're using is the information from all the points around it to see where it points, right? So the limit's more like a pointer using information gathered from around it, okay? Now, we can focus on one side of limits, but we also can bring it together to both perspectives. Like you'll see here at the end is what we're going to do. So focusing on -3, if we approach, -3, I'm looking at -1. Approaching -3 here. If we go from the left-hand side and we look at all these values, they're pointing to that Y value there. Okay. So hopefully we're in agreement here with that one actually equaling -1. Now remember this one here, we were coming from the left-hand side, so that's why we only focused on these points over here. Now, if we do the right-hand side limit now, which you'll see is the second one here, and we look at all the points that we have here, again, they're pointing to, in this case, -1. Now, what we see here is there's agreement between both perspectives, right? When your left-hand limit and your right-hand limit agree, then you can say, hey, the limit of X approaching -3 is going to be -1, okay? So whenever you want to find a limit, let's just say like, hey, go find the limit as X approaches -3. It's going to be important to make sure you consider both perspectives, okay? Any questions to that first one? All right, then the second one here, we want to make sure we're careful, is that we recognize that there's a little bit of a difference going on here. Now, instead of focusing on -3, we're focusing on -1. As I approach from the left hand, this one actually approaches +3, okay? So say, hey, that's +3. But when we approach from the right-hand side here, all these points are pointing down to -2. This is a situation where we don't have disagreement. We don't have agreement, sorry. So we would say, hey, this particular limit does not exist, which can happen. Okay, it's definitely something to watch for. Here I use an example of a piecewise function. In a second, we're going to look at another example. But one thing I want to make sure to add to this that's very important for us setting up ourselves for some of the calculus we do is what we're going to call continuity, right? So as we look at if f is continuous, so looking at continuous or continuity, oh, didn't mean to click that. So continuity is saying that as I go through a graph, there's no breaks that keep me from moving forward in that graph. Okay, so it's going to be an important aspect that we want to watch for. Limits is how we define that. Now, what we need to show is that the limit of f of x as x approaches a equals f of a. Now, remember, the limit is using information around to point to a particular value, where here with f of a, we're just evaluating it. What we find here, though, if you look at this particular problem for -3. Our limit did have agreement, so we actually had a limit as x approached -3, which was -1. Now, if we look at our graph though, and we say, hey, what is f of -3? We can go and plug it in and see, hey, there's a point right there that happens to equal -1. Okay. Because these things are the same, right? We can then say that, hey, f is continuous at x equal to -3. Okay. Now, visually inspecting the graph, we can then start picking points outside of that. We can see that those would also be continuous. The part that we definitely would want to focus on is where this break occurs. All right, that's definitely things we want to focus on. We want to find places where, hey, we might run into issues. Now, keep in mind, I designed this graph so that this first one worked out nicely. But then when we focus on this one, we end up getting a limit that does not exist. Once you show that the limit doesn't exist, or this is not true, as I said, the limit and then evaluating is not the same, you would say, hey, the function is not continuous at that value. So make sure you see here, this would be an example where it has discontinuity. But this one here is because the limit does not exist. Okay. Now, I'll definitely jump into continuity a little bit more, but I just wanted to make sure to show from that perspective there to kind of set us up for what we need later on, right? Continuity is definitely an important part of the definition. Some of the homework problems ask you to determine if something is continuous. Just make sure you remember to go through the process of finding the limit. That's the first thing you need to do. If your limit exists, then go plug in that x value and see what happens. If you can plug the x value in and get to the same value that your limit gave you, then it is continuous. That's what you want to take from that. Okay. Things to watch for, though, as I mentioned, is if the limit doesn't exist. That's kind of a good step to say, hey, this graph is not continuous at this particular point. Right. Other things to watch for, as I mentioned, let's say you do all your work and you say, hey, the limit as x approaches 5 of g of x equals 3. But when you go do g of 5, you get 7. So the limit when we approach 5 points to 3, but when I plug in 5, I get 7. That would be another example where we would say it is not continuous because these two values are not the same. Okay. Anything clear for somebody?
I think someone is confused about where the -1 come from.
The -1 for this -1 or the one that we got from the limits?
I don't know. I see in the chat that somebody asked about the -1.
Hey, it was the one that came from the limits.
Yeah, so when you look at x equal to -3, we're focused on approaching this value from both sides, right? Now, what you see is if I use all these points and I follow that line, it points to that. All these values are pointing to this individual ordered pair, right? That ordered pair happens to be at the y value of -1. So we're taking the y value. Remember, we focused on the x value because that's what we're approaching is x equal to -3. So when I look at that all these values point to that particular y value. The same thing on the other side. As I use all these x values, sorry, those y values continue to point to that ordered pair that we're using here. Again, the y value of that ordered pair is -1. You have to remember here that oftentimes when we're using functions, we have to separate the domain and range for what we're talking about. So the limit here is focused on the domain as we approach from left and right. So we're trying to get closer to -3. The graph, though, approaches this particular ordered pair here, which happens to be equivalent to the y value of -1. That's where the -1 came from. Now, remember this one here, the last one, since both of these equal -1, then the overall limit as x approaches -3 is going to be -1. Does that help?
Yes.
Now, again, I just picked -3 here. We could have used any value. So like I could have said +1, right? I could have put -4. Just make sure you see here, like if we're looking at x approaching +1, I would use that dotted line, just kind of give a quick reference to show, hey, this is where we're going. We're trying to approach that line from the left or the right, but we're interested in following those ordered pairs. And hey, look at that. It points to this particular ordered pair. So this time instead of -1, that would be +2 at that point. And the same thing would be true from the other side. Now the quadrat got a little steep there, so it was a little bit tougher to see. Okay. Now, what I will say is just make sure if you're having trouble on the homework, let me know. Okay. As I mentioned, yeah, limits are important for what we're doing, and it's good to have the practice with them, but make sure to take kind of what it's doing. It's not evaluating, it's helping point to something. Okay. Now, there are some situations though where we're going to have to look at a function and evaluate the limit, and we don't have the graph. Okay. One nice thing about this is you could always jump in and try to do a direct substitution. Now, direct substitution is not always going to work. Okay. What we see here is I have a quadratic function and I want to find the limit as x approaches 5. Okay. Well, if you remember, when we look at the quadratic graph, oops, we get that parabola shape is going to look something like this. And we can have confidence in there that, hey, as I look at this, there's no discontinuity, right? We now have a way to go and prove that through what we just talked about, but we don't need to prove that. We can just say, hey, there's not going to be any discontinuity here. So guess what? Let's try direct substitution. So let's just see what happens when we take our x value and plug it in. All right. Well, when I do that, I get something that I can use the order of operations to simplify down. I get the value of 17. Well, the nice thing about that is what we see here is from direct substitution, I actually get a value, which is a real number and everything. So I can conclude then that, hey, through direct substitution, I do have a limit that I can evaluate. Now, if we needed more proof, right? If someone said like, "Oh, prove that to me," then you could definitely go to the graph, show them that, hey, as I approach from the left hand, I'm going up to 5, it points to 17. As you approach from the right hand, it points to 17. Therefore, the limit is 17. But no, that's not something we always have to do. Sometimes we just want to make sure we can evaluate it to get to the value that we need. Okay. Always read the problem and what it's asking for is what I would say there. Now, the things you have to watch for, though, let's go look at this next one now, because the next one says, hey, let's find the limit as x approaches 3 of this rational function. Well, what happens is if I try to do a direct substitution with 3, I'm going to get into a situation that kind of messes everything up. So if I do that, I'll get a 0 on top. And I actually get a 0 in the denominator as well. Now, at this point, you might be alarmed by the 0 in the denominator, but we're going to call this as the indeterminate form. What that means to me is that I can't really do anything with it, right? It doesn't help me at all. So trying to do a direct substitution did not work in this case. Now, this is also a hint, though, that you should try something else. Okay. What is something we can do here becomes a question to change how it looks. All right. Well, if you remember something that we looked at the other day, right? Sometimes we need to simplify rational expressions. So let's try to simplify that and to see what happens. So we got indeterminate form when I tried to direct substitution. Let's try to then simplify it and see what we get. Well, simplifying this here, let's do our factoring. So let's do a quick little table here, a times c. All right, so the nice thing here is we can use -3 and -5. So we are able to factor this, okay? And what you're going to find here is the thing that helps us even more is that when I factor this, we actually can simplify. Now, understand again, the problem was designed to allow us to simplify, so you're not always going to be able to. But when you go try to do a direct substitution, just plug that value in and you get to something, oops, like we see here, the indeterminate form. Simplifying might be one thing that can help you here, okay? As we need, I'll make sure to show some other ones, because if you remember, there's times where you might have to rationalize a denominator when you have radicals involved. That would be one example where you might get the indeterminate form and we need to do something to make it work. Here, however, once we simplify, we can say, hey, x minus 3 is divided out to 1. So this limit can now be written as x approaches 3 of 1 over x minus 5. And we now have something where we could just say, hey, if I plug in the 3 now, we get what? 1 over negative 2. So this limit equals negative 1/2. Now you have to be careful here. Remember, this is a limit. This isn't me evaluating the function. If we try to plug in 3 into the function, we have to make sure to acknowledge that, hey, x cannot be 3 or 5. We can't plug in 3 or 5. So we can't evaluate the function at 3, but what we just found is that I can get a value with the limit using the points around 3, okay? Now, the 5 is a whole nother story. We'll have to talk about that one later. Any questions with this with these two? Now, keep in mind, like I said, that when you're asked to just evaluate a limit, try the direct substitution first to see what happens. Just be ready for situations where you get like the indeterminate form. 0 over 0 doesn't mean anything to us. So we try to simplify to see what happens. Okay. Now, this next problem here, all right, we're going to focus on that situation, like I said here. I kind of ignored the 5. I focused on the 3. So let's focus on that next part. So this function, I have 2 over x plus 2, and I want to use the limit to approach x equal to negative 2. Now, this one's special because, again, if you go look at your restriction, x plus 2 cannot be 0, so x cannot be negative 2. All right. So I cannot plug in negative 2. So this is where the limit helps us out. Now, the difference here is we can't simplify this. So if we try to do direct substitution, we would get that 2 over 0, which doesn't help us, right? We would say, hey, there's nothing good there. Okay, you can't divide by 0. Not going to help me. All right, so let's take the table approach, right? What that means is I'm going to take this limit and I'm going to break it up. We're going to look at it from the left-hand side. We're going to look at it the right-hand side and see what happens. All right, now the reason I'm breaking it up is just so that we can get a better understanding what goes on with the overall limit, okay? With that said, though, if we take a table approach, I'm just going to make a quick chart. We're plugging in x values, and we're going to evaluate the function. I'm just going to call the function f of x, okay? With that said, though, if we're approaching negative 2 from the left side, we can start at, say, negative 5, and then go to negative 3. And then let's just get closer and closer. So let's do negative 3.9, negative 3.99, and just for the fun of it, let's do 4 nines. Okay. Definitely going to want your calculator on stuff like this because that's going to be what's helpful. I would also encourage you to use something like Excel. Excel would be a great tool in this situation to help us out. Okay. building quick tables. If that's something you would like to see, please let me know, and I'll definitely show you how to get those formulas up. Because the nice thing about it is you could actually put that function into Excel and just have it evaluated for you. Using my calculator though, I'm going to put 2 over the x plus 2. Just know that use your parentheses and then put the first number instead of x when you use your calculator. And let's go knock all these out. So for -5, if you do that, you'll get -2 over 3. If I plug in -3, I get -2. Now, things to kind of watch for here. They're both negative numbers, okay? 2/3, though, is smaller than 2, so we actually went further down in negative values just now. So let's keep going, -3.9. So that gave me, I went the wrong way with this, y'all. I'm sorry. That shouldn't be like that. I apologize. It should be -2.1. We're getting closer to -2 from the left side, not the right side. -2.01 and then -2.0001 to get those 4 digits. That was my apologies. I messed that up. So trying this again, let's do, instead of 3.9, that went the wrong way. We're still going from left to right here. That's why I had to change it. We're doing -2.1 now. And I get -20. -2.01 gives me -201 over 100. -2.0001. Oh, I'm totally messing this up, y'all. All right, sorry. Messed up my calculator when I was plugging in, going too fast. When you plug in -2.01 should be -200. And then when you do the -2.0001, we get -20,000. Now, this is something that you do want to watch for, okay? As I mentioned, be careful to see my mistake that I made over here so that we're paying attention to what we're doing, right? I had 3.9 and 3.99. Well, what happened is I was going left from -5 to -3, and then I turned around and went the other way. So I shouldn't have done that. Okay, we wanted to get closer to -2, not -4. That was a mistake. So that's why I had to switch it to these. Okay. Now, looking on this other side, what you're seeing here is it started at -2/3 and it's growing rapidly. Now, what you're going to see, the closer that we get to -2, the bigger that value is that we're going to get outputted. Okay. What we're going to say here then is as we grow here, that's just going to approach infinity, right? It's just going to keep on growing and growing and growing.
I'm sorry, could
Now,
you scroll
math,
down a bit? We can't see the bottom of the screen.
see what?
Could you scroll down a little bit? We can't see the bottom of the screen.
I can't scroll. It's fully zoomed out. That might be your computer. Is anybody else having issues seeing the full chart?
I can see just fine.
Okay. Well, I'm not able to scroll zoom out anymore. So check your Zoom on your screen, please, if you're having issues. But the key is to understand that when you plug in these different values, I'm going from -5 approaching that -2. Right? So I plugged in -3 and then I plugged in that -2.1 and so on. We keep getting closer. So we're not actually plugging in -2. We're just trying to get as close as we can. Okay. What you need to see here though is the rapid growth of these values. And I was saying that as these values grow, the way that we'll kind of sum that up mathematically is using our infinity symbol. That, hey, as we approach -2 from the left, we're going to approach not just infinity, we're actually going to approach negative infinity because all those values are growing in the negative direction. Okay. Now, it won't happen all the time, but there's different situations where we should expect the result of infinity. Now, if we take the same approach, though, and we use the other side, this time I'm just going to do -1, -1.9, -1.99, and -1 and then 4. Let's do 4 nines. All right, so we're going to plug in these values real quick. Let me make sure I do it correctly this time. Hopefully, when you're doing these, you're starting to see kind of similarities, though. All right, as you look at these two charts, they're different. They are different, but they're not completely different. Okay. Now, I didn't bother using the same approach with the -5 over here, so I kind of cut that point out with this chart. But what you're going to find is these two charts have similarities, okay? One's approaching from the left side while the other is approaching from the right side. That's what you're seeing here with these X values, okay? Both of these Y values, though, show that there's a little bit of symmetry kind of going on with how the graph behaves and being irrational. If we talk about parent function stuff, we could explain that. If you do need to see more stuff from graphing functions, just kind of better understand where we come from with some of this, just let me know. I do have those video links from my in-class lectures for the college algebra. Okay. So as we see here, though, the big difference is these are all positive values growing rapidly. Okay, I haven't put in -2, but if I kept growing the number of nines I put at the end, it's just going to grow the number of zeros we have. Okay. So what we see here this time, though, instead of approaching negative infinity, it approaches positive infinity. Okay. What we find here is that means this does not exist as far as the limit. Right? Those do not agree, as we mentioned before. Since they don't agree, the limit doesn't exist. The other thing you find here that if we wanted to dig deep further is we just found the definition, a mathematical definition to what we call an asymptote. Okay, so if I do a quick sketch of this graph, we said we can't use -2. What we'll see here is that when we go graph it, oh, what I do? Sorry, just kind of quick sketch of it. Our graph is going to look something like this. And what we mathematically defined here is approaching this value from the left side. As you see here, it's going down to negative infinity. And then as we approach it from the right side, we see here it's going to positive infinity. That would be the mathematical definition for a vertical asymptote that we have on a rational function. Okay. The main thing I want you to see here, though, is that be prepared for your results to be infinity. Okay. And a table is a great way to help you there. If you get stuck, try a table to see what happens. That's always a great way to go. Okay. Is there anything I clear up here for y'all? As needed, I can definitely do more where the result's infinity. There's different situations, as I mentioned, that I will end up discussing because as we deal with exponential functions and polynomial functions, we can use that for different purposes. Okay. The next thing I want to look at then is what happens if I use the limit as x approaches infinity itself. So as we look at that graph, right, if I'm trying to talk about this function, what happens is I try to go to the far right end of this graph. That's what both of these are going to be talking about. Okay. Now, of course, as I'm doing positive infinity, know that you could also do negative infinity, right? We could go down and say, hey, what's the limit as x approaches negative infinity. Okay, I just focused on the positives for today, just kind of as an introduction. Now, what you're going to find here is that we run into some situations where we can kind of play around and do some quick substitution, right? What you're going to find that when you try to do quick substitution, like this 9 will stay a 9. But if you try to go to infinity with this or this, right, it's just going to go and grow and grow and grow and never stop. The thing you have to focus on is now going to be the power of a term. What that means is x cubed has a greater power than this negative 7x. Okay. With that said, then we look at coefficients too, right, to kind of compare stuff. But right now, what you're going to find is if I look at this, the main term we need to focus on is this x cubed. And if you remember, just kind of a quick sketch of x cubed, then let me do that one. Sorry, y'all. Just kind of a quick sketch of x cubed looks something like this. As we approach the positive infinity direction, okay, this graph's going to just grow and grow and grow. Okay. And since nothing's going to stop it, that means this limit then just equals positive infinity. Okay. If you remember, this is what we called end behavior in college algebra, right? Another way that that would have been mentioned is what we call rise. The right-hand side of this graph rises. We just have, again, a better way to write this. The limit notation allows us to write this out in a more formal mathematical way than we were in college algebra. Now, with that said, though, as I mentioned, we could also change this up and say, what if we say negative infinity, right? Just to make sure we have that example. Let's bring this down. All right. Again, what you need to make sure you pay attention to is, as I said, is the term with the highest power. So we have a polynomial, x cubed is the highest number here. Because that's odd, the thing that you want to remember here is whenever you have an odd degree, the two ends are going to be different, right? So you're going to have up and down whenever you have a positive coefficient, like we see here. Well, let's say like you had negative 7x to the fifth. All of a sudden, it changes, right? Because what's going to happen here is think about negative 1. If you cube it, you get negative 1. Those are things to kind of keep in mind when you start dealing with your exponents that like, hey, even the result's always going to be positive. But whenever I get odd, a negative input will give me a negative output. Okay. So what you see here is when I try to say this approaching negative infinity, hey, each of those negative numbers I cubed are going to become negative. So the result here then would equal to negative infinity. It's going to grow continuously with nothing stopping it, but it's just going to be going downwards rather than upwards. And you see that here with this graph, that as we go to the right, it goes down forever. The way that we discussed that, though, in college algebra, we said, hey, that means it falls. Rises and falls. Any concerns with that one from a polynomial perspective? Okay. And one thing I hope you take from this is just I'm trying to get it introduced. Okay. As I mentioned, we'll definitely need this when we deal with exponential and logarithmic functions. So we'll definitely go back and kind of talk about this a little bit more then. But I felt like this was a great way to connect it back to something that you've discussed previously in college algebra. Okay. Again, dealing with vertical asymptotes. Now we have a more formal way to write it. Here's another example of taking something that we work with, the end behavior of polynomial function, a more formal way to write it. Well, if you saw on my graph over here, sometimes we deal with end behavior of rational functions. If you, in college algebra, many of you probably heard horizontal asymptotes. Well, let's go look at a more formal way to write that, because that's what the next one's looking at. Hey, here's a rational function. How can we work with this? Now, what happens here with rational functions, we have a nice way that we can manipulate what's going on. Because if I try to do that direct substitution we talked about, both of these are even, right? So whether I plug in a positive number or a negative number, it's going to spit out positive. So I get to the situation where I have infinity over infinity. The way that we call that, though, again, is going to be that indeterminate form. Okay, that's an indeterminate form like that 0 over 0 was. So it's like, hey, I can't just jump straight into this. Well, the nice thing about this, what we can do is divide every term by the variable with the highest exponent on it. So we're going to take our limit as x approaches positive infinity. We're going to say, hey, let's take all these, what the heck just happened? All these terms and divide it by x squared. We're distributing, I have no clue what's going on, y'all, sorry. The x squared, 1 over x squared, basically, to every single term in the problem. The reason we like this, though, it gives me something that's going to be nice to work with. Okay. This is what we're going to focus on. Whenever you deal with this here, we're focusing on just the limit as x approaches infinity of 1 over x. I know it's x squared, but x, as long as you have x there, we're going to simplify there. What happens as this denominator gets bigger and bigger and bigger is what we want to look at. Well, let's do a quick table. If you take x, and we're just doing 1 over x, we plug in, say, 10, 100, and let's plug in 10,000. You get 1 over 10, 1 over 100, and 1 over the 10,000. What you're going to see the pattern here is you get 0 0.1, 0 0.01, and then it's what? 0 0.123, 1. Let me make sure yeah. Okay. You're just going to keep adding more zeros and putting that 1 all the way to the end. At some point, the number is going to get so small, it's going to be indistinguishable between the number and 0. And remember, we're dealing with a limit right now. So we're not actually trying to evaluate it. We're just trying to see where it points to. So what we find here is that, hey, this particular limit that we're looking at, as that number grows in the denominator, it's going to just end up pointing at 0. And we can use that here with this problem. By doing this division, we can isolate that one term to have the fraction where that's my only variable now, and it's in the denominator. With that 9 on top, this is just going to grow to 0. As it grows and grows and grows, it's just going to approach 0. Well, the nice thing about that is now I have a way to evaluate this one, right? I can go in and say, hey, if that's approaching 0, then this limit here just equals 3 over 1, which is equal to 3. Now, it's not going to come up all the time. Please keep that in mind. Like I said, I'm just making sure to introduce the process. Okay. What you see here, though, again, is limit involving infinities. All right. It's going to grow rapidly. So you can have a polynomial situation where it grows without bounds. But keep in mind, you can also have a rational situation where now there's something that's keeping it from growing. Okay. Now, I did some manipulation to get to this point here, but we like this because now I can compare this back to just a basic rational function, kind of like that parent function in a sense. So keep in mind, I use this table to show that these values are just going to keep getting smaller and smaller and smaller. So that's where I'm getting the 0 from. Okay. Now, the reason that's helpful is now we know that, hey, on the far right end of this graph, my values are going to approach 3. Now, they're never going to get to the 3, as we talked about here, but that's what they're going to approach. And if you remember, this is what we call the horizontal asymptote when we talk about rational functions. Okay. Yeah. Any questions or concerns there? All right, then as we close out today's class, some things that I want you to be familiar with and just kind of be comfortable with using a graph to evaluate limits. Make sure you took notes for continuity, recognizing that, hey, if my limit equals the value and that I can plug that value in and get the same thing, then the function's continuous at that particular point. Okay. Try to do direct substitutions when you're evaluating the limit you're given. You will run into situations where you have to try something different though. So make sure you remember stuff like simplifying. Okay. There's some other things that can come up. If you get stuck on one, just let me know. Like I said, limits are important for the calculus, but we're not going to do limits all the time in this course. So it's good practice, just kind of get an idea and understanding, but it isn't crucial to everything we do. So if you get stuck, make sure you reach out to me, please. The next step, though, I wanted you to see here is where do limits help us, right? So this was formal definitions, but make sure you see here I used the table to kind of just show you how infinity gets involved as a result. And then we use this to show how we can use infinity with our limit itself. Okay, so I went back to parent functions to kind of help with that. Right, I know this one had a little bit more going on, but I wanted to make sure to show, like, if you remember how to get the horizontal asymptote, we talked about the ratio of the leading terms in college algebra. So that's where I came from with that one. If you don't have any questions though, and you've put your first and last name in I see a couple people join. So if you haven't put your first and last name in chat, please do so before you leave so I can update the attendance. If you don't have any questions though, have a great weekend and everything should be good for Monday. So I'll see you Monday.